I already post the slide on the classroom on demand. Okay, from chapter 7 to 15. Um, we just want to change, okay, to do something in different way, okay, so then everything will not be the same, okay, so just change the seat a little bit, something that easy to change, okay. What we're gonna do 3 weeks from today, on every Friday, okay, we will have class participation score, okay. Okay, so we will randomly choose someone to answer, okay, whatever I discuss in class, okay. So if you are chosen to be person to answer, you're supposed to answer. If you cannot answer, I deduct your participation point, okay, just like a quiz. Think about it, one quiz, okay, and it's not like right or wrong. I don't care the answer that you try to answer it wrong or not. This is the thing that we are learning. Okay, you can answer anything wrong, but as long as you try to understand and try to answer. Okay, so I give you 5 points for this quiz already. If you can answer, your score remain 5. But if you are picked, okay, and you cannot answer, then your score decrease by 2, or maybe by 3. Yeah. Chance very slow that within 3 weeks that you're gonna be picked twice. Okay. The first time I deduct 3 points. 3 points. If you pick again, you deduct 2 points. Okay. So we're gonna randomly choose who's going to be the person to answer. Okay. Question come anytime during the class. Okay. On any of these slides. Okay. 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 The reason because again last week on Wednesday we learned, okay, I saw like half of the class, okay, fell like to sleep, okay, feel like you're getting lost from the material, okay, maybe because of me, I'm not doing my job well, okay, or maybe because of you, or maybe because of environment, whatever it is, we try to change, okay. So we will do some kind of class participation. Okay, again, I already give you 5 points. Okay, but if you do not answer, then you get deduct. Okay, your score. So let's begin and then we continue. Okay, only 3 weeks, only 3 Fridays, put it this way. Okay, this will not happen on Wednesday because the room on Wednesday is like hard to arrange. Okay, first one, randomly pick now. Okay, number, I don't remember your number. Okay, this is random. Next time I'm gonna use like some kind of program or Excel to randomly pick. Number 28. Okay, what is this one? What is this one? Yes, what is it? What is it? Example buddy system. Okay. Buddy system is a mixing between fixed size and varied size partitioning. Okay. Let's say the next person. 38. With 38. 38. 38. No 38. How about 48? Okay, 48. Okay, explain more. He said it is, actually his answer is not totally right. Okay, but he said it's a mixing, buddy system is a mixing between fixed, okay, partitioning and dynamic partitioning. But what is it? It's just this one. What is this one for? Buddy system. System. Okay,พี่แอน deduct 3 point just try to answer whatever you know okay okay maybe not okay I will start ask you question from the new material that we're going to learn okay okay maybe next person okay this person will not get point off either okay but just let's begin okay let's say 12 okay this number 12 here 12 okay what is this one 12 no what is it first what is it what we learning in this chapter no this chapter what is this chapter is about memory management but this system is memory management okay that mixing between dynamic and fixed site partitioning okay it's not totally fixed okay because it can change okay but it change in certain value like what value what kind of what size 2 power by n okay the size cannot be just anything okay 2 power by n okay good number what else do we have any number in here here number okay whoa 85 too big 42 42 okay tell me is there any internal fragmentation or external fragmentation in this system or not is there any internal and external fragmentation external give me example which one is external fragmentation did it left outside okay let's suppose if one process 500k coming in it's going to occupy this one and then after that if we have 100k coming in we have 64 but actually I should not say external because it's too big but if we have let's say 2 of them that very small okay let's say for example if this one is occupied and this part also been occupied if these 2 were occupied then if we have these 2 left and if we have let's say 150k coming in 150k cannot fit here or fit there and that part we call external fragmentation the part that we have left okay if we don't combine them together we cannot give to a big process okay but if we combine them together they're big enough okay it still have external fragmentation okay but it's likely to be less severe after one process finish they're going to merge okay the body together okay so then we have big space again okay now another part of the question do we have internal fragmentation where A need only 100k but we give A 128k we have 28k left that we will not use agree A need only 100 but we give A 128 so 28k left unused that internal fragmentation okay but the advantage of this one is that okay the memory could be managed in dynamic okay sometimes you can have big space to be ready okay if not so many process coming in you can let the big process coming in okay okay so far we don't deduct point of anyone okay give okay but after this next slide is a new one then we're gonna start deduct your point if you cannot answer okay all right what the next one this is the way that we can implement the data structure okay to point to each of these partition okay we can build a binary tree okay to point to each partition okay and this binary tree can also help us determine the body okay, of the partition space. Like for example, who is the body of this part? It's this one. And if you look at the tree, these two share the same parent. Okay, so then we would know that the body of this one is who? Body of this node, you look at the parent, you know where is his body. Okay, the key that we need to know the body is that in body system, when one process finish, okay, that memory is become available to the system. System will merge its body. Okay, if its body is available. Okay, so that's why each node, okay, will show whether that node, okay, point to the space that is occupied or not, is allocated or not, or that node, okay, is unallocated, that space. Okay, and or maybe that node on the tree represent not the space but represent the way that two nodes could share, could be the body, which is this node. Okay, so the non-leaf node, okay, showing the body. Okay, this node tell that these two are body. Okay, understand? But again, let's say if 64 left, if C left, okay, if C left, the body of this one is this one. So it means that both of the space available, we're going to merge them, become 128. If we merge them to 128, what would happen to this one? What would happen to this node? If I merge these two together, become 128K available, what would happen to that node? Huh? This node will change from the shading to white space because it becomes pointing to the space that no one using it. It's allocated. Understand? Good? Okay. We don't need to random. Understand? Okay. Maybe we have the random program. Okay, the random will be PN job. PN will random, not me. Understand this one? Move on. Okay, one question. PN random number. ไม่มีเครื่องนั้นเหรอโอเคมาเปิดไม่มี not random yet. What happened if let's say all process finish? Okay, what happened if all process finish? Okay, let's say random number. 93. I don't have 93. I pick the last two digits of your pen. 62. 34. 34. 34. What happened if all process finish? What happened to this? What happened to the memory? And what happened to the tree? If all process finish? Every node will be purple. Okay, which color? Okay, okay. Whoa. Every node will be white. If all of them finish. The node on the top will be white, allocated. And what happened to other node? What happened to other node? No more. Agree? If all of these finish, all the memory will be merged together in one single piece. If all of them one single piece, then you're going to have only one node. No more any other node. And that top node or the root node will have the white color because it's going to be the unallocated. Only one allocated. The size is 1 megabyte for this example. Good? Okay. What is your number, Anthony? You have number because your number could be different from not in the order. 37. 37. Okay, just in case if we, yeah, there might be 37. Okay. So if we random number 37, then two of you have to answer. Okay. Move on. Understand? Body system. Okay, so you not only, okay, the way you manage, okay, the way that Unix use body system, the way they manage, they build a binary tree like this, okay, to manage the memory. Okay. Okay, one more example. Why binary tree? Why binary tree? แตงกวา cucumber. Okay. Why binary tree cucumber? You know why? Okay. Why binary tree? Okay, handsome man. I don't remember your name. Because the way we divide memory, we always divide by half. Okay, when we keep divide by half, the binary tree is the one that can split into binary. Each node have 2 children at most. Okay. And all of them, after you divide, okay, you're going to have one node occupy and another node maybe not occupy like this. Or one node is occupied, another node is a parent of, okay, 2 part of the memory. Okay, or could be 2 like this. Okay. Understand? Okay, that's the body system. Okay. Again, body system, okay, it help memory management, okay, to become more systematic. Okay, and the way to manage, we use the tree to, okay, help point to the space in the memory. Okay. Now the next issue on the memory management is addresses. Okay, how can we refer to that memory? Again, to refer to the memory, okay, we have 2 parts. Okay, the one that the way you refer to the memory according to the program itself. Okay, and another one you refer to the memory, the actual memory, we call physical address. Okay, and we can also, okay, refer it relatively. Okay, from one point, okay, you're gonna refer 5 instructions after that relatively from the point that you point to. Okay. So the way that you're going to calculate the actual location, okay, you have to translate from logical to physical. Again, logical is understood by the program that you want instruction number 5. Okay, but instruction number 5 could be anywhere in the memory. Okay, so you need, okay, to translate from location of instruction number 5 to the actual memory. So to translate that, you need to have something we call relative address to show the first part of the program or the first part of the process. If the process starts from this point, instruction number 5 is 5 below under that. Okay, so we need to know the relative. Okay, I show you this one later on. It's adding. The next technique of memory management, and it is the one that used right now with the modern technology. They use something we call paging. Okay, paging is a way that to manage memory similar to the fixed site partitioning. Okay, but the difference between fixed site partitioning and paging is that the process that going to store in the paging mechanism, you must the process may occupy many pages. Okay, unlike fixed site partitioning, you have one partition. Each process can occupy only one partition. Okay, and that have the limitation because process cannot grow bigger than one partition. Okay, so this one try to compromise with that problem that the process should be bigger than, okay, the size that we partition. Okay, so here we can have many partitions we call page. One process can be located in many pages. So we try to cut down the problem that OS limit the size of the process. Now OS would allow the big process to be able to use the system. Okay, because again the memory will be divided into many pieces they call frame. Okay, one big part of memory divided into frames, similar to the fixed site partition. Okay, but among these frames, okay, one process can use many can allocate in many frames. Okay, so a process itself also be divided. Okay, process divided into pages, and we put one page of that process into one frame in the memory. And if the process have the second page, we also load the second page into another frame, third page into another frame, okay, and so on. Okay, so frame is a term of how we divide memory, okay, by the OS. The page is how we divide program, okay, also by the OS. Okay. Okay, yeah, look at example. Okay. Let's say process, let's say at the beginning, when the system starts, okay, OS will divide memory into frames. Okay, for this example, let's say OS divide its memory into 15 frames. Okay, to be ready for the process to load in. Okay, and let's say the first process coming in, process A. Let's say, that's an example. Let's say one frame is 1K. Okay, let's say the first process A, let's say process A is 4K. So process A will be divide of 4K into 1K, 4 pieces. And we're going to load these 4 pages of the process into these 4 frames. Understand? Okay, process A will divide into A0, A1, A2, A3 in 4 pages and load into these 4 frames. Okay, and let's see next later we have process B that need, let's say 3K. So we divide B 3K into 3 pages and load each of those pages into the frame number 4 to 6. Okay, and then let's say process C coming in, it needs 4K. So we divide into 4 pages and load into the memory frame. Okay, so here if B finish, B can leave. Okay, when we finish, B leave, these 3 frames become available again. Okay, so OS will mark that here these 3 frames are available, and also this one down here. Okay, and now let's see the next process D coming in. D need, let's say 5K. D gonna be divided into 5 pages. Okay, and let's say some of them load up here, 3 of them, and 2 pages are down here. Okay, so D need 5 frames because D have 5 pages. Understand? Okay, so that you can see that, okay, D, I mean one process doesn't have to be consecutively together between frames. Okay, some page might be somewhere here, other page of the same process might be in different place. Okay, understand? Okay. Let's say if C left, what happened? Okay, random number พี่แอนไม่ต้องเปิดก็ได้บอกผมnumber we add random here 27 okay 27 who is 27 okay what happened if C finish down here so far continue from here if C finish when process C finish what happened C go out who go out okay C will go out when C go out what happened to memory which one available C if C finish 7 to 10 will be available okay if C finish 7, 8, 9, 10 and 13, 14 are available frame agree okay and let's say what happened if E come E need 5 frames where can I put E E can be 3, 4 of them here and another one maybe down here. Okay, so a process will divide into many pages. Okay, and each page can be loaded any available frame. Okay, understand? Okay. Okay, now next question. And random, tell me the number. Do we have internal and external fragmentation or not? Huh? There might be some internal. Okay, good. Why?
So if your program's 4.5.
Because let's say, for example, okay, sometimes the last page might not need the whole frame. Okay, let's say, for example, if process A needs 3.2, just an example. If they need 3.2, this one going to be occupied 1, 2, 3, and this one use only 0.2. And then you have 0.8K left unused. So that is internal fragmentation. Okay, but this internal fragmentation will not be very big. Why? Because one frame is small. It guarantees that your internal fragmentation will not be larger than the size of the frame. Okay, let's say for this case, if it is 1K, internal fragmentation will not be bigger than 1K. Unlike fixed size partitioning from the beginning. Okay, fixed size partitioning from the beginning. And frozen. Okay, the fixed size partitioning could be any size, okay, up to the way that we partition. ทำไมมันค้างวะพี่แอนไม่ต้องฟรีก็ได้จึ๊กแอนฟรีตรงไหนเนี่ยไม่ไปOkay, okay, if you look at the fixed size partitioning, tick here. Okay, if the process is super small, let's say for example, process need only, let's say 2 meg. Okay, you're gonna have 6 megabytes left unused. Okay, even though you divide it into, let's say 1K. Okay, if your process is very, very small, it still left a lot. Okay, so the partition, okay, if you have divide into fixed size and the size is big, when you have super small process, you're gonna waste a lot. Okay, so for this example, if my process A needs 3.2, if my process A needs 3.2, I'm gonna use only 3.2, and then 4.8 down here gonna be left unused. Okay, but if you compare with the paging, if process A needs 3.2, I don't waste 4.8, but we waste only 0.8 down here. Okay, so it still have internal fragmentation, but very, very small. The maximum internal fragmentation is equal to the size of one frame, less than a little bit. Okay, at most. Now the question is, do we have external fragmentation? Number, P.N., what number? 37. Oh, okay. So Antonio, you answer another 37. Okay, 37. Do we have external fragmentation? No, good. Okay, we will not have external fragmentation. Whatever hole you have left, okay, because one process gonna be split in many pages. Okay, so if your process is big, your process gonna split into many pages. Just like for this example, like D. Okay, we have these 3 frames and 4 frames left. Okay, the new process D bigger than 3 and bigger than 4. Okay, but it still be able to load in because it's less than the total of 7. Okay, because D will be divided into 5 frames. Some of them be loaded here, some of them are loading in there. Okay, so no external fragmentation at all. Whatever you left in the frame you left, you can use them. Okay, unlike body, okay, or vary length. Okay, whatever you have left, sometimes there's in many places, but one process has to be together. Okay, so this is a good thing of paging system. you always divide process into many pages. So then some page can use some part, other page can use different part. Doesn't have to be together. Okay? And that's why they use in most of the operating system right now. Okay? Paging. Understand? Okay?
Because is if I design ผมภาษาไทยแล้วกัน ถ้าเกิดว่าผมดีไซน์เป็น1 กิกช่องละ1 กิกและคราวนี้ผมเอา process A เป็น3 ไบต์ process B เป็น4 ไบต์ก็เลยใช้ไม่ได้
Good. Okay. Your friend asks, what happened if we choose the size of a frame very big? Okay, if you choose the size of the frame very big, what happened? You're gonna have a good chance to have big internal fragmentation. Okay, that's why OS, when they divide memory into frames, they don't choose the big size. Okay, they don't choose like 1 gig like that. Because when you have small process, you're gonna waste a lot. Okay, but why don't they make it very super small? Why? You're gonna see in the next slide. You may see why. Okay, I mean obviously, if one frame is super big, you're gonna use only so little when you have small process, and you're gonna have internal fragmentation very big, which is not good. Okay, we try to cut down internal fragmentation. Okay, but what happens if a frame is super small? What do you think? Let's say many of these use many K. Okay, let's say you design 1K, it's only 100 bytes. Just an example. Okay, this one gonna need like, let's say 3.2, you're gonna need like 32 pages, 32 frames. Okay, that one is, let's say 4.9, you're gonna need 49 frames. If the one frame is very small, one process gonna have many frames. Gonna need many frames. What's wrong with having many frames? In terms of managing one process, okay, it's likely to be longer because now you are one process. You could be many places. Okay, it's different in very far away. Okay, so it's harder to manage the process if you divide frames super small. Okay, to cut down the internal fragmentation. Okay, the OS usually, okay, they don't try to make the frame size to be too small or too big. Okay, likely like 1K or 500 bytes. Okay, this is the same thing for the database too, if you still remember. Anyone remember when we create DB2 database, if you still remember? Okay, database also divide the way they manage the data in the memory into page also. Paging is not only mechanism for OS, it's also mechanism for the application or software. OS is the software that needs memory. Database. Okay, database also try to reserve memory into different parts. Okay, so they also divide the memory of the database into pages like this. Okay. Page table. Okay, let's see. Maybe this one can answer your question easier. Okay. What is the page table? After we have these frames and we load process into many frames, or the process itself also divide into many pages, the question is, how would OS know where is the location of that page of each frame? Of that page of each process. Because one process may have many pages and load into many frames. The question is, where are they? For example, where are the frames of the process D? Where are they? Where are process D? The frames, the pages of process D. Process D had been divided into 5 pages, load into frames 4, 5, 6, and 11, 12. Okay, OS have to manage, have to be able to find out where are page 1, page 2, page 3, page 4, and page 5. Okay, so which frame? Okay, and that is the page table. Page table is a table, okay, managed by OS, okay, for each process. One process, okay, OS will keep one page table to that process to determine where are the pages, okay, of that process. Okay. For example, here, if you have many processes, each of them will have their own page table. Okay, the page table will show that each page located in which frame number. Okay, like for example here, process D, okay, was located in frame 4, 5, 6, and 11, 12. Okay, so this one telling us that page 0 of process D is at frame 4. Page 1 of process D is at frame 5. Okay, so this is the one that OS maintained, so that OS would know, okay, where are the location of pages for each process. Understand? What happened to B? Empty. Why B is empty? Why B is empty? Look back. At this time, do we have B? No more B. Okay, so actually B should not be empty. You should not have that page table for B anymore. When B finished, okay, page table of B should be disappear because no more process B in the system. Okay, but I just try to show you example. Okay, that at this time, okay, we should not have anything in page table for B anymore. In other words, no page table of B. Understand? Ready? Now, after we understand this page table, we should be able to map between logical address to physical address. Okay, here come. What is logical address? Logical address is address that understand by the process itself. Okay, each process, okay, need to have address, okay, of each instruction. Okay, for example, okay, let's say I have process, let's say I use process D. Okay, let's say process D, okay, need how big of D? 4 point something or at most 5. Agree? Okay, so process D, if you look at the process itself before you load into the memory. Okay, process D, let's say gonna start with instruction or data from location, let's say 0, 1, that's an example, 1, okay, actually 0, 0, 0, 1, 0, 2, dot, 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 dot. Okay, if you have, let's say 4.8K, okay, at the end here should be, okay, location, logical address around 4799. That's an example. This is the last address, 4798. That's an example. Dot, 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 dot. Okay. First look first. Actually, more detail than this. Okay, if the process D, okay, had a size of 4.8K, okay, process D gonna have instruction or data at instruction and data 0, 1, 2, 3, 4, 5 until 4799. Agree? The question is, this one, some part load up here. Okay, some part load down here. Okay, but this is the real memory. They have physical address. Okay, in terms of program said, I want to use data on the third logical address. Question is, where is this address? Where is this data in the real memory? Where is it? Okay, use your eye. Can you tell? Where is the data or instruction 0002? Can you tell? It's somewhere around here. Why? Because the first 1000 instruction, let's say it is 999, 1000, just an example, actually 1024. Okay, but I make it simple one. 999, 0 to 999 will be on the first frame. Okay, and then the second 1000 from 1000 to 1999 will be in here. Okay, and then 2000 to 2999. Oh, running out of space. 2999. Okay, a lot more. Okay, it's on the third. Okay, 3000 to 3999 is here. Okay, and 4000 to 4799 is here. Agree? Okay, so that is a physical address. Okay, so actually physical address also have the address Okay, let's see this one. Have the address. This is the real address. Okay, let's say the real address is 0000000. Okay, let's say 60. Okay, this is 0. Oh, this is a frame number. Sorry. Okay, the physical address will be, the first one is 00000. That's an example. Down here, let's say this is 1K. That's an example. Physical address of this one will be 00100. The first data there, 1000. Agree? Until 1999. Again, for simplicity, I use 1K mean 1000. But actually, in the real data system, they didn't use 1000. It's 1024. Okay? What is the first physical address of this one? Of the frame 2. 2000. 200. Agree? The last one of this one is 2999. And the first one of this, 3000. Okay? And here, 4000. The first address of this frame is 4000. Okay? But actually, in terms of logical address of process D, it address what? 0. Okay? So we have to be able to map from this logical address 000 to change into the actual address 4000. So that we would know exactly where is this one in the memory. Understand? The program, okay, will look at, go to this instruction. I mean the program. Sometimes your program have if, jump to that instruction, go to that instruction. Okay, the program know only their own address. We call logical address. It's address, okay, that understand by the program itself. Okay, but in the system we have physical address. Okay, that understand by the hardware and the actual address. Okay, so if we going to, let's say, execute instruction number 2 of this process D. Okay, we're going to need to execute instruction number 2 of process D. Okay, the third instruction. Okay, OS have to map this one into the physical address, which is what? This is the logical address. OS have to find out where is this one in the real memory. Which one? Is for this example 4002. Good. Agree? Okay. Let's say somewhere here. This one address, let's say, for example, 1254. Where is have red color? No. Let's say this logical address 1254. Where is this one in the memory? From 1254, it actually load in what frame number? 5. So this one will convert into 5254. Good. Now explain to Carrot, because Carrot doesn't understand. Why 5254? Because this is first page. Agree? One page, 1K. This is the second page. This is the third page. This is the fourth page. This is the last page, page number 5. Agree? Okay. This is the second page. Okay. And from the second page, we go down to 254 location after that. From here, we're going down from 000 to 254. Agree? That from the bottom, from the top, go down for 254 cells. Okay, the same thing with this one. We go down from here, 254 cells. Okay? Again, this is the second page. Okay, second page is located here. Okay, and we go down for 254 from there. From the beginning of second page, it also means from the beginning of this frame, we go down for 254. But this is the frame number start with frame number 5. And then 5, 254. Understand? Okay? Okay, another example. Let's say address, let's say this one, 2684. Where is 2684? If 2684 is a logical address, what is physical address? This is the page number 1, 2, 3. Actually, page 0, page 1, page 2. If we start from 0. Page 0, page 1, page 2. Where is the page 2? Page 2 is here. And page 2 start from the top is 6,000. Agree? So the answer is from the 6,000, we go down for 684. Understand? All right, the end. Random number. 6, 56? 56. Okay. Tell me, if logical address is, let's say, 3333, where is it, 3333. Okay. 11, 3, 3, 3. Good. Because page number 3, page 0, page 1, page 2, page 3. Page 3 is located in frame 11. Understand? Because page 3, this is page 0, page 1, page 2, page 3. Page 3 is located in frame 11. Understand? That's how we translate. Okay? But again, you look at the memory. Actually, OS doesn't look at memory like this. OS look from where? OS cannot search the whole memory. OS translate from logical to physical by look at the page table. Where is page 3? Page 3 is on frame 11. And it is 3. change to 11. Okay? Or for example, this one, page 1. Page 1 is at frame 5. So they change from 1 to 5. The last 3 are the same. Understand? Or this one, address 2684. 2684 implied it is page 2. Page 2 is in frame 6. So they just change 2 to 6. 684 are the same. Understand? So OS need to use page table to help translating from logical address to physical address. Okay? The program dealing with logical address because program doesn't know where the program is going to be located in the memory. Understand? Okay? Okay? Okay, a little bit before we go in detail. Let's say, for example, this program finished, D finished, and let's say someone execute D again. Okay? When you execute D again, D might not be in here. D might be in any of these frames. Okay? Let's say next time, just an example. Okay? Let's say 2 hours from now. Okay? A finished, C finished, whatever finished. Okay? I load program D again into this memory. Okay? Let's say I have my D1 here, D0 here, just an example. D1 here, D2 here, D4 here, D3 here. Let's say maybe D2, D1, just whatever reason. Okay? OS just load these 5 pages in here. D0, D1, D2, D3, D4. Okay, just an example. Okay, what is my page table of process D? My page table for D. What look like? Let's say again, D finished, A finished, C finished. Okay, and then user run D again. Okay, actually, this is not really D. It's going to be a new page number, page ID. But anyway, just an example. Okay, if user run process D and process D has been located in here, what the page table look like for new D? Page number 0, 1, 2, 3, 4. Again, the same program. This program needs 4.8K. Okay, it still needs 5 pages the same way. Okay, but now where is the page 0 now? You need frame 0, page 1, frame 5, okay, page 2, frame 2, page 3, 10, page 4, 8. Agree? Now, with this new situation, where is my address 1254? In the program, logical address is 1254 with this new page table. Where is my 1254? 1254. 5254. Okay. What happened to this one? Instruction 2648. Ooh, exactly the same. Okay, 2684 the same. Okay. How about this address? Or maybe this one. 3333. 10333. Okay. It depends on where the process is loaded. Okay, into the frame. Sometimes they load in the frame like this. Okay, or sometimes they load in the frame like this one. Okay. Because one process, you run again and again, it could be in any place or any part of memory. Okay? This time it located in these frames. But this time located in these frames. It could be different. Understand? Okay? Okay, this is just the kit number. The actual number is in binary number, the address. Okay, it's not gonna look like this, but it looks like this. Okay. Ready? It is the real address. Okay, again, this is logical address first. Okay, let's say it is one process. Okay, doesn't say what process number. Anyway, let's say it is a process. Okay, one process may divide into pages. Okay, let's see for this example. Okay, if OS divide memory into frames. Okay, each frame is 1K. Okay, if one frame is 1K, the question is, okay, one frame is 1K. How many things we can load in here? The K is not the. I should not say. Let's suppose, okay, one instruction is 1 byte, just for simplicity. This is 1 byte, 1 byte, 1 byte, 1 byte. Oh, actually, not really 1 byte. The size of this one is whatever it is, okay. The size of one instruction, it depends on what type of machine you use. For example, when you said 64-bit computer or 32-bit computer, right? When you buy computer, you buy the hardware. You buy hardware, you consider the CPU. And they said this CPU is 64-bit or 32-bit. And the OS should follow that, the hardware. That's why you have 32-bit window or 64-bit window. The term 64, 32 is this size. Okay. The size of one location in the address. How many? What the size of the data that you can store for one data? Okay. But anyway, let's say if I want to store, okay, this one in one frame. Okay, I want to store 1,000 things, 1K. 1,000 things in here. Okay? How many bits do I need to identify 1,000 things? Actually, 1,024. How many bits do I need to identify 1,024 things? The answer is 10 bits. Okay? I can refer to any of these among 1,024 cells if I use 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I need 10 bits to refer to this one. Yes or no? Yes or no? For example, if I have 8 things in here, how many bits do I need? To identify things in there, I need 3 bits. This is 001, 000, 001, 010, 011, 100, 110, 101, 110, 111. Agree? If we have 3 bits, okay, address, 3-bit address can refer to 8 things in here. Agree? Okay, so if I going to identify 1,024 things in here, I need 10 bits. Agree? Okay, 2 power by 10 is 1,024. Okay, so here, if I divide one page, okay, one frame of memory or one page of the process, okay, that can store 1,024 instructions or 1,024 data together, instruction or data. Okay, I need 10 bits to refer to the thing inside the page. Understand? Okay, 10 bits to refer to 1024 things. Okay, now I have 10 bits for this, 10 bits for this, 10 bits for this, 10 bits for this, to refer to inside of the page. Okay, now after that, if I have, let's say, 3 pages, that's an example. Okay, how many bits do I need to identify 3 pages? 2. Agree? If I have 2 bits, I can identify page 0, page 1, page 2, page 3. Would be page 00, page 01, page 10, page 11. Agree? Okay, so it means that to refer to the data or instruction in the page, okay, I need last 10 bits to identify the thing inside page. Other bit in front identify the page number. Understand? Last 10 bits to identify what inside one page. And then the rest in front identify the page number. For example, this is last 10 bits identify inside. In front of this bit 11, okay, this is 1. 1 means page 1. Okay, so it means this page 1. And then the last 10 bits identify whatever that address. Let's say this one is 412. This is going to be 412. Or let's say this is 478. Okay, they already translate. This one, okay, if you convert from binary to decimal, it's 478. So this one means this is 478 from the top to here. Okay, but on the page number 1. Understand? What I show you here, this is all decimal number. For example, my 684 here is supposed to be a binary number, just like this binary number. Okay, the 684 there. Okay, whoops. 684 254 333. Okay, supposed to be, sorry. Okay, supposed to be the last 10 bits like this. Understand? And again, this is logical address. It address understand by the program. Okay? Ready? Move on from here. This is still logical address. Okay, now, if we want to map from logical address to physical address, we do the same thing, the one that we just did. Okay, that we mapping between page table. Okay, for example, what is 2684? We just did. 2684 is implied page. Oh, sorry, let me use something else. 1254. 1254 on page number 1. Page number 1 map to frame 5. Okay, so here 1 change to 5. 254 the same. Same thing with this one. If the last 10 bits, okay, it's just like my 254 here. My 254, when I try to map from logical to physical, they are the same, 254, 254. Same between logical and physical. The same thing with this last 10 bits. It will be the same in physical. What we need to change is to change from page number, look inside the page table. Page number 1 is in this frame. So we change from page number here into the frame number 00110. While the last 10 bits remain the same. Just like this one. 254 remain the same. 333 remain the same. 684 remain the same. Understand how to map from logical address to physical address? Okay? All right, and random number. 17? Okay, I'll be and random 17. 17, who is it? Okay, 17. This is logical address. Okay, of this process. Where is this one in physical address? Show me physical address. Huh? Zero what? I think it's wrong. I can walk here, you cannot see. One, zero. Okay, one last chance. Huh? Can I event? Huh? 011. 011, then 0. 0. 1. 1. 1. 1. Good. Agree, everybody? Carrot, not carrot. I forgot her name. Next to nut, nut. Next. The one that look like carrot. Green. Agree, green? Tell me, how does it work, green? How does it work? Yeah. Which one you use to compare with page table? First 6 bit. Why first 6 bit? Okay, good. Because the last 10 bit determine what inside the page. Agree? Let's say if I said one frame is 1K. If one frame is 1K, I need 10 bits to identify inside the page, also inside the frame. And then after this, there is 10 bits. And then the bit in front identify the page number. So this is page number 2, right? 10. So we look at page number 2. Address of the frame. The frame number is this frame number. Sorry. This one. Okay, good, green. Understand? Okay. Okay, let's see what happened if one frame contains 2K data. This one frame Okay, contain data of 1K, data and instructions. How about if OS, okay, divide memory into 2K, 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 what would happen? Okay, if the same address, okay, this address, okay, if the memory design one frame is 2K, what happened? The same address here. Okay, number we add 41. Okay. 41 with 41. 1 0 0 0 0 1 0 1 1 1 0 0 0 1 0 1 0. Okay, 41. The same address, but one frame is 2K. With 41. No 41? Okay, we add random again. Oh, green? Oh, the same. Oh, she already answered. Somebody else? Okay. Huh? Oh, really? 33. Who is 33? 33. If one frame is 2K, can you translate this one into physical address? Let's suppose if the page table looks like this. If the page table, actually the page table should change. Okay, a little bit change. But let's say if the page table is like this. What is physical address? How many bits we need to identify inside the page or inside the frame? How many bits do we need? 11 bits. Good. We need 11 bits. So what does it mean? From the back, 11 bits. From the back. 11 bits the same, which are 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0. This is 11 bits. Agree? It is the 11 bit. And then what next? And then what page number now? Page number, what the value here? Page number 1. Agree? Write the page number 1 if we have that page table. Write page number 1. 0, 0, 0, 0, 1, 1, 0. Oh, should not be like this. Should have only 5 left. Okay. If it's the same memory, if we divide frame into the bigger size, okay, so it means one page could have less amount of, one process could have less amount of pages by 1 bit. Okay, it should not have this one anymore. Otherwise, it's unusual. If it's the same memory. Okay? Understand? Okay. That's the paging. Okay. Okay. Before the end, I show you one more thing, and then we're done. A little bit. Maybe we're gonna finish. Okay. The next one, okay, is another, okay, technique for the memory management. It's called segmentation. Okay. What the difference between segmentation? They are the same. They are memory management. one process can be divided into many parts, just like many pages. And also memory also divide into many parts, just like many frames. And we load them in. It's almost the same with paging. But the difference between paging and segmentation, okay, is that the size, okay, could be vary. The size of each segment, okay, or in other words, the size of page and frame could be vary, not fixed. Like this one, if we fix with 1K, all frame going to be 1K, 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 1K. Okay, and all, if you stick with 2K, all frame, all pages in this system will be 2K. Okay, but segmentation is not. It could be vary. Some frame small, some frame big. Okay. Oh, I don't have table. I don't have example. Let's say, for example, if this is segmentation, okay, just example. If this is segmentation, this one doesn't have to be 1K. Some of them have K, 0.8K, 0.9K, 1.2K. It could be vary. Okay. If the size of, they don't call pages, they call segments. Okay. If each segment could be vary, why do we need that? What's the benefit of that? No internal fragmentation. Because let's say, for example, if process A needs 3.8 or 3.2, they're going to be 3, 3, 3, and this one exactly 0.2. They will not give 1K. Okay, so they get rid of internal fragmentation. Okay, so that's the difference between segmentation and paging. Okay, the size that we divide a process into many segments, it could be different size. Okay, but there is a limit, maximum. Okay, otherwise they're going to divide one process in just one segment, which is not good. Okay, they try to split them many places to try to get rid of external fragmentation. Okay, so there is a maximum size. Okay, but each of the segment could be vary. Okay, but if we do that, the way we translate from logical to physical is different. Okay, you cannot use the simple mechanism. Okay, that last 10 bits the same, only the front bit. Okay, change from page to segment, page to the frame. Okay, it doesn't be like this, not this simple. Okay, it depends because now the frame could be any places. Okay, because it could be on any memory cell. Okay, for that case, when you try to map, okay, you must know, okay, that where is each segment start. Okay, start from where. Okay, and then from that point, we're going to use that one to calculate. Okay, like for example, okay, if this is a segmentation, okay, the size could be vary. Okay, let's say they limit, okay, the size of one segment to what? Can you tell? What the limitation? What is the maximum of each segment? 4K. This one tell. Agree? They limit one